Everyone, hopefully you're having a good weekend, and I hope you can hear me in the video even though there's wind. I'm working on one of the problems on the review that's asking you to find the power of a complex number. So in order to use Demoivre's theorem, you need that complex number, to be in polar form. So the very first thing we need to do is work on converting it to polar form. The first thing I'm going to talk about is where is this point initially. So we're looking at the point 1 minus I. That means if I plotted it on a rectangular coordinate system, it's going to be in quadrant 4. That's going to be important when we go to find our angle. So it's just good to know how to visualize that point. You don't necessarily need to graph it. To get it into polar form, we need both the r and the theta value. So for r, we're going to use square root a squared plus b squared because we're looking for its distance from the origin to that point. So plugging in our values for a and for b, we get our r value. For theta, we're going to plug in b and a as if they were y and x, because when we plotted them, b corresponded to the y values and a corresponded to the x values. So that's going to be -1 over 1, which gives me a tangent of -1. Now over here I've got my r value. Over here I need to find the angle. What I need is the theta, not this number over here. I need the angle that has a tangent of -1. So really what we're calculating is theta is tangent inverse -1. So I'm looking on my unit circle and deciding where is the tangent equal to -1. And that actually happens at two places, either 3 pi over 4 or 7 pi over 4. And of course one of these lines up with our point, so that's the angle we're going to use. Now once I've got those two, I can write this in polar form. That format is always r cosine theta plus I sine theta. So plugging in my r and theta, I've got polar form. Okay, so once we've got our polar form, then all you have to remember is the rules for Demoivre's theorem. This theorem is actually going to be given to you on the test, but it's just two simple rules. When I'm raising a complex number to the power of anything, we call this our power of n, then we're going to raise our r to the power of n and multiply the angle times n. So I'm going to do that now. I'm raising my complex number, z stands for the complex number, to the 9th power. So I'm going to raise the r value to the 9th power, and I'm going to multiply the angle times 9. Okay, so over here is where I had a little shortcut. 2 is actually being raised to the power of 1/2, being raised to the power of 9, so that's 9 over 1/2, which is the same thing as 2 to the power of 4 times the square root of 2. Now when I multiply the angle, 9 times 7 is 63. And over here, 2 to the power of 4 would give me 16. And over here, looking at my angle, yes, I found my angle. There's not really a way to simplify that fraction. However, we want our angle to always be between 0 and 2 pi. And now if it is 0 or 2 pi, I would lean towards 0. So we want to include 0 but not 2 pi and keep it underneath 2 pi. So I need to find an angle that's equivalent to that, but much, much smaller, so that it's within one full circle. So off to the side, I'm going to do a little bit of work. I need to take the 63 pi over 4 and subtract away enough 2 pi's until that number is less than 2 pi. Because subtracting away 2 pi's gives me the same place on the unit circle, but it's one full circle smaller. So I'm going to go ahead and do that real quick. If I subtract away 8, I would get 55. Subtract again and again, so this time I'm going to multiply 8 times something bigger. Let's do 5 full circles. So that's going to give me 15 pi over 4, still too big. So subtracting away one more full circle gives me 7 pi over 4. So my final angle for this is going to be 7 pi over 4. And that is my final answer.